Okay, well, I'm really happy to introduce Madeleine Udell. She's an assistant professor of management science and engineering at Stanford University with an affiliation with the Institute for Computational and Mathematical Engineering and a courtesy appointment in electrical engineering, and is currently on leave as associate professor with tenure of operations research and information engineering at Cornell University. She studies optimization and machine learning for large-scale data analysis and control with applications in marketing, demographic modeling, medical informatics, engineering, system design, and automated machine learning. She's won numerous awards for her work, and I'm only going to mention just a few: the Alfred P. Sloan Research Fellowship, an NSF Career Award, an Office of Naval Research Young Investigator Award, the Informs Doing Good with Good OR Award, and other grants and awards. We're quite excited and appreciative to have Madeleine here for the 1W-Minds seminar. Madeleine, please take it away.
Great. It is a pleasure to be here. Thanks, everyone. I'm going to tell you about how to use low-rank approximations to speed up optimization. I'm really excited about this research agenda, and we see sort of potential for using this in all sorts of areas of optimization. I'm going to tell you about 3 today. I'm happy to sort of speed up or slow down depending on what people are interested in or excited about. So feel free to interrupt with questions or not in the usual Zoom style. Either way goes. This is joint work with 3 of my students. Zach Frangella has been leading this. He moved with me from Cornell to Stanford. Pratik is at Stanford with me, and then Shipu is graduating from Cornell and about to start at Amazon. And then also the first part of this is also joint work with Joel Trop, my postdoc advisor and longtime collaborator. Okay, so let me tell you the big idea. The big idea is that randomized numerical linear algebra allows you to use order n, allows you to approximate a matrix vector product with an n by n matrix in time order n, right? Normally that would take you order n squared. You can do it in time order n, okay? Even better, you can approximate linear system solve with an n by n matrix in time order n, okay? Normally that would take you time order n cubed, okay? So that's way faster than the basic operation. So if your algorithm uses a large matrix and that large matrix is approximately low rank in some suitable sense, and there are many senses, then you can speed up the algorithm. So here are some examples that I'm going to tell you about today. One is an algorithm we call Nystrom PCG, Nystrom preconditioned conjugate gradient, that can solve linear systems using a randomized low rank approximation as a preconditioner. Second thing I want to tell you about is a method called nice ADMN that you can use to solve composite optimization problems. These are things like minimize, a smooth function that depends on data applied to your variable, plus a function that's easy to take the prox of, or maybe it's a projection operator, g of x. This models problems like lasso, regularized logistic regression, or support vector machines. So for these kinds of problems, using nice ADMN, which is taking advantage of randomized numerical linear algebra, is allowing us to beat the state-of-the-art solver for each of these problems. And it's kind of extraordinary to me that the same algorithmic framework can possibly sort of be the best current algorithm for each of these. And the last thing I want to tell you about is a method we called sketchy SGD for finite sum minimization. In a sense, it's a stochastic quasi-Newton method. It uses a low-rank approximation to speed up a solve of Newton system or quasi-Newton system. It seems to have better robustness compared to first-order methods. It's easier to choose parameters of these methods, and it's faster than other quasi-Newton methods. So it seems to have the speed of first-order methods with the robustness of quasi-Newton methods. And you can even use it for deep learning. So as a preview, let me show you what that looks like in the context of deep learning. Okay, so imagine we're doing classification with a neural net. We are going to take, we're going to look at the CFAR10 data set. So this is a image data set, but we're going to look at the tabular version of the data set, which means we're not using convolutions. We're just putting a multi-layer perceptron on top of the image data. Okay, and let's consider using Atom to train the neural network, which is probably the state-of-the-art, thing that people would do. Okay, so if you do this using learning rate 0.005, here is how the test accuracy changes as you train. Okay, each epoch is one full pass through the training data, so it gets a little bit better and then kind of, I don't know, oscillates around. If I used a different learning rate, like learning rate 0.01, then I would get different behavior. In fact, the test accuracy would basically go down and then plateau at a low level. If I used a different learning rate, it might just stay at the same low level. Okay, so I really like Atom isn't a standalone solution. You need Atom plus hyperparameter tuning. It's not enough to use Atom. Okay, and that means look, I was actually able to get a good one, right? Using learning rate 0.001. Okay, so you can't just look at the runtime of Atom. You have to look at the runtime of Atom plus hyperparameter tuning, and it's a little bit fiddly. Okay. Let's try this method called Sketchy SGD, which is using this stochastic quasi-Newton update, which I will tell you about later. This is just a preview. Okay, we try it with learning rate 0.005, and here's what we get. We try it with learning rate 0.01, and here's what we get. We try it with learning rate 0.02, and here's what we get, right? We try it with learning rate 0.001, and here's what we get. Okay, so Atom is doing all these weird things, and we have a method that is substantially more robust. Okay, so that's pretty exciting, and it's not very much slower than Atom, tiny bit slower. Like, okay, that's parameterizable. So somewhere between 1% slower and 30% slower. Okay. Okay, so using higher order information improves the robustness. Okay, so let me start slow with basically I want to tell you about how to find randomized low rank approximations. Then I'm going to tell you how to use them in linear systems, how to use them in composite optimization, and how to use them in stochastic optimization. Okay, so here's the basic building block. It is an efficient way to approximate an eigenvalue decomposition, top K eigenvalue decomposition, using randomized numerical linear algebra. So let's say we're given a matrix that's positive semi-definite, an n by n matrix, and we want to find a good rank S approximation. Here's my suggestion. Draw a random Gaussian matrix with S columns. Okay, we're going to compute a randomized linear sketch of our data matrix, so A times omega. So you can think, how hard is that? It's basically S matrix vector products with our data matrix. Okay, now we're going to form the Nystrom approximation, which once we have the sketch, actually we don't need more access to the data matrix. Okay, so given the sketch Y, I can form this Nystrom approximation like this. It's written, using a pseudo inverse. I don't recommend that you write your code using a pseudo inverse. Instead, you can use a small Telskin EQR and a small SVD to sort of construct the same thing algebraically. Okay, the properties of this approximation. So number one, it only needs matrix vector products with A. So if you have sort of streaming access to A, or you have Oracle access, or somehow it's hard to access A, this is a kind of nice thing to do. The total computation required is just S matrix vector products with together with something that's order ns squared. Okay, so linear in n. The total storage required is also linear in n. The approximation is always symmetric positive definite. Its rank is always less than or equal to S. And it's always a lower approximation to A in the loner order. Okay, so all of its, A minus A hat is always positive semi-definite. Great. Okay. How good is this approximation? This certainly sounds much easier than full eigenvalue decomposition. How well does it work? Let's say A has eigenvalues lambda 1 through lambda n. And we're going to define the P stable rank of A this way. You can see this as sort of a sum of the eigenvalues that are larger than the pth eigenvalue, sort of approximately. Okay, it's a sort of smooth version of that. Or a count of the number of eigenvalues larger than the pth eigenvalue. Pick any p that's greater than 2 and set a sketch size that's about twice as large as p. Okay, so there's something funny. We need a sketch size to be larger than the rank that we're trying to the rank that we're comparing the approximation with. Okay, okay. We're going to draw a Gaussian random test matrix that has S columns and construct the Nistrom approximation. That approximation is going to, well, think about this. If we had the best rank P approximation, right, then the error in our approximation in the spectral norm would be like lambda P, okay? That's not what we get here, right? Number one, we're using a rank S approximation, not a rank P approximation, where S is about twice P, okay? And we're not quite getting the error we would get with the best rank P approximation. Instead, we're getting the error of the best rank P approximation times some other factor. Okay, that's generally, not too big, especially when your matrix has strong spectral decay. Okay, right. So we say that the error of the randomized rank S approximation is comparable with the best error of any rank P approximation. Okay, so that's the basic primitive we're going to use. Maybe it's also worth saying that if your matrix happened to be exactly low rank, so if lambda P was equal to 0, then of course you've exactly nailed your matrix. Okay, and this is true for any P, right? Your fixed S, okay, any P. So if there's a P, for which as long as you've chosen S greater than P, then you exactly nailed the approximation. That's a nice thing to know. Okay, let's see how to use this primitive to solve linear systems. Here's the problem that I'm going to consider, a regularized linear system. So we're going to try to find x so that a plus mu I x is equal to b, okay, where a is a symmetric positive semi-definite matrix and mu is a positive number. The eigenvalues of a, again, are going to be lambda 1 through lambda n. The condition number of a is the ratio of the top to bottom eigenvalue. Okay, that's an important quantity because it controls how fast many iterative methods for this problem converge. The regularized matrix is the one, right, that's the one that really appears in this problem. It's a plus mu times the identity. And it always has a condition number that is at least as good as the condition number of a. Okay, so the bigger the regularization, the easier it is to solve this linear system. Okay. And I'm going to write mat vec of A for the time to compute the matrix vector product AX. Okay. If they were sparse, this would be the number of non-zeros in A. Okay. Why would you solve a regularized linear system? Once you start looking for it, they are everywhere. Okay. So for example, iteratively reweighted least squares, you're solving a sequence of these problems. Kernel ridge regression, you're solving a sequence of these problems. Gaussian process regression, you're solving a sequence of these problems. Approximate cross validation, you're solving a collection of these problems. To compute influence functions, how much does each data point influence the final classifier that you construct using a variety of different machine learning algorithms? That's also a linear system. Hyperparameter optimization, you can even pose as a linear system. So the list goes on and on and on. Interestingly, in some of these papers, they propose kind of funny methods for solving these linear systems. So it's good to sort of take a step back and say, how should you solve a linear system like this, where A is a data matrix, and we expect the data matrix to have strong spectral decay. Okay, so how would you think about solving this? So the first thing you might think of is a direct method like Cholesky. Okay, you factor A into like a lower and upper triangular matrix. Both of those are easy to solve, right? To do a triangular solve, and then you solve it. Okay, so this takes order n cubed flops for a dense matrix and requires entry-wise access to the matrix A. So that's fine as long as A isn't too large, maybe even up to, size 1,000, maybe even like bigger than that. It does fine, but for very large scale matrices, this is not a great idea. For larger scale matrices, you will probably want to use an indirect method. Okay, so something like conjugate gradient. So in conjugate gradient, the main work per iteration is to form a matrix vector product. So applying A to a residual R. Okay, so at the kth iteration, conjugate gradient has the property that it finds a solution X, a putative solution, that's in the kth Krylov subspace. That means it's in the span of the right-hand side, A times the right-hand side, dot, 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 dot. And to get to epsilon accuracy, it's going to take you square root of the condition number of A times log 1 over epsilon matrix vector products, also iterations of CG. There's a third method that I've seen people use, especially in the context of machine learning, which is a series expansion for the inverse. This is a little bit funny because it turns out the series expansion for the inverse, either Neumann or Taylor series, lives in, if you look at k terms of this, it lives in the kth Krylov subspace. Okay, and so it is provably worse than what you would get using CG. Okay, because CG is actually optimal within this subspace. So I don't recommend using these series expansions. Okay, so here's a really simple idea. If I had a low rank approximation of my matrix, why not just solve a linear system involving that low rank approximation instead of the original matrix? Okay, so I'm going to solve something with the approximate A instead of something with the exact A. Okay, and that's going to give me an approximate solution instead of the exact solution X star. Okay. Now, there's something sort of great about this idea. Probably the biggest thing that's great about this idea is that I can apply the inverse in time that's linear in the side length n. Okay, because the inverse of this low rank plus constant times identity matrix, I can just use Sherman, Morrison, Woodbury, and I can write out the inverse explicitly in terms of the eigenvalue decomposition of my low rank matrix A. Okay, and the Nystrom approximation procedure like it already constructs this eigenvalue decomposition. So I have A in this sort of eigenvalue form. Okay, so I can just write this down immediately. Now, again, shouldn't write this down, right? Don't write it down. You don't want to multiply out V and V transpose. That gives you an n by n matrix. That's not what you want, right? But you can apply the inverse to a vector, and you can apply it in order n times s time. That's great. It works well as long as the right-hand side is actually in the span of these top k eigenvectors. Okay, but if you want high accuracy in general, you need the sketch size to get quite large. Okay, so for high accuracy solutions, it's not a good idea. Okay. Now, for low accuracy, it's actually excellent, and I'm going to show you how to. In fact, this is going to be the main idea that powers our results for stochastic optimization and deep learning, right? Where actually each subproblem you do not need high accuracy. Okay, but it's good to know how to get high accuracy too, because sometimes you do need high accuracy. Okay. So to get to high accuracy, we're going to need to use a different idea, which is preconditioned conjugate gradient. Okay, so we already talked about conjugate gradient. What's the idea of a preconditioner? So a preconditioner is any positive definite matrix P. Okay, and here's the idea: is if AX is equal to B, then it's also true that P to the negative 1/2 AX is equal to P to the negative 1/2 B. Okay. Now I'm going to do one change of variables in order to make a symmetric matrix appear. I'm going to replace X by P to the negative 1/2 Z. Okay. And when I do this, I see a new symmetric matrix right here: P to the negative 1/2 A, P to the negative 1/2. Now, why would I want to do this? I'd want to do this if the new matrix that appears has a much better condition number than the original matrix, right? Because the convergence rate of conjugate gradient depends on the condition number of the matrix, right? So now I've figured out a way I could recover the solution X from a solution Z, and I can get a solution Z, right, just by applying this matrix. And I can get a solution Z by solving this new equation, which has a new matrix, which has a new condition number. Yeah. Okay, so how do I get So right, the two things that I need, right? I need the new matrix, this guy, to have a good condition number, and I need P to be easy to invert, right? Because I'm going to just apply the inverse to the -1/2 to Z. So how should I precondition? Most common heuristic is Jacobi preconditioning, setting the preconditioner to be the diagonal of the matrix A. Another thing that people often use is an incomplete Gillespie decomposition. So sort of K steps of a Gillespie decomposition, and using that, which works well for structured sparsity because it can preserve sparsity. There's another idea that comes out of the randomized numerical linear algebra literature called sketch-in precondition. Okay. Now this stuff works if you already have a factorization of your matrix A. Okay. And in fact, people generally consider a setting where this factor, the inner dimension of the factor is longer than the outer dimension. Okay. So where basically the X transpose X looks kind of like an inner product, but it's creating an n by n matrix, little n by little n matrix. Okay. And what they do is they pick a sketch size to sketch down the inner dimension of this matrix. Okay. And they use that to construct a preconditioner. Unfortunately, it sort of works in a rather limited setting because this procedure is already order n cubed flops. Okay, so it doesn't work if this n is actually very large. You have to be in a sort of very careful setting where like this n is much, much bigger than this n, but this n still isn't too large. Okay, so it's not going to be what we want for the problems we're considering. Let's think about what would it mean to be an optimal low rank preconditioner? Okay, so let's imagine that we have a best rank S approximation to the matrix A. Okay, we did a exact eigenvalue decomposition and took the first S eigenvectors. Okay, if you wanted to make a best preconditioner using this information, what would you do? Well, you would try to flatten the first part of the spectrum. Why? Right, conjugate gradient depends on the condition number, right? That's the ratio of the top to the bottom singular value, eigenvalue, okay? So the top one, you would like, if you only have access to the top K eigenvalue decomposition, all you can operate on is this part. And the best thing you can possibly do is make it flat, okay? That reduces the ratio between the top eigenvalue and the bottom eigenvalue as much as possible. Okay. Okay, and the way that you make it flat is like this, okay? So our preconditioner is going to be the top K approximation of your matrix, scaled down so that the plus sort of identity on the rest of the rest of the basis for the space, and that makes sure that these eigenvalues get appropriately tamped down relative to the eigenvalues that you've left out. Okay, so given a rank S misnorm approximation, okay, so maybe not the exact approximation, we're going to define what we call a Nystrom preconditioner exactly analogously, okay? So we're just going to plug in the Nystrom preconditioner instead of the optimal one of rank K. Okay. And we're going to use the fact that we've got a regularized linear system, and so the regularization enters right here. Okay. The inverse, again, can be applied in linear time. Let's see how it works. So this is a data set near MSD. It is rather large. I'm using rather small regularization. That means it's a hard problem. Okay, and I'm using a sketch size of 500. Okay, so here's how conjugate gradient works. That's the orange line, and you can see linear convergence. Okay, down to numerical accuracy. Here's how Jacobi preconditioning works. So if I precondition with the diagonal of A, I actually get worse performance than if I didn't precondition at all. Okay, and that's not unusual behavior for these machine learning problems. Okay. In contrast, if I precondition with the Nystrom preconditioner, I get, again, linear convergence at a much, much faster rate. Okay, so I get down to numerical accuracy within like 150 seconds. I also have on here, how long would it take you to solve this problem with QR? It's not unsolvable. Actually, it's kind of fine. But it does take 1,000 seconds as opposed to 150. Okay, so you probably better to do this. And for many problems, you don't need this level of accuracy anyway, right? So QR is really overkill for a lot of problems. Okay. Awesome. Going super slow. That's okay, but okay. It means I'm going to skip a lot of the theory, I think. Okay, so NIST PCG can control the condition number. In fact, you can show that the condition number of the preconditioned matrix is bounded by something that depends on the error in your approximation and the first eigenvalue that you left out, lambda s, okay, or your estimate of the first eigenvalue that you left out, which is nice because that's an actual computable quantity. Okay. So that means that for large enough sketch size, you could actually get this condition number down to anything you want, up to down to like 3, for example. So you can get quite strong results. Like the condition number can be bounded by a constant, which means it takes a constant number of iterations times log 1 over epsilon to get to the accuracy epsilon. Okay, how do you get the error to get that small, right? In fact, sort of the optimal error is when the error is proportional to the amount of the regularization. So how do you get that? Oddly, it works decently well across a wide variety of data sets just to use a fixed sketch size. Like sketch size 50 works well. Actually, we've taken it down even farther, like sometimes 10, sometimes 5. It can provide a surprising advantage. And that's because many of these matrices from machine learning have really strong spectral decay at the beginning. Like the top eigenvalue might be, 5 times larger than the next one, which is 5 times larger than the next one, which is 5 times larger than the next one. And then they kind of tail off. Like it flattens out actually relatively quickly. So just doing something that operates on just the top part of the spectrum can be really powerful, give you a huge speed up without a lot of extra work. Okay. There are other ways, that are sort of more formal that you can do this. We have a prescription for an adaptive rule that increases the sketch size until the estimated error is small enough. And it adds 1 dimension to the sketch in order to verify that it has achieved the error that it needs. And you can also use an a priori bound on the sketch size to ensure that the error that you'll make will be of order the regularization parameter. Okay. I'm not going to tell you about that because I'm going too slow. Okay. Here's how it works in experiment across a number of different data sets compared to a number of other randomized preconditioners. In general, you can see the NIST preconditioner is taking fewer iterations and it has a shorter runtime than other comparable methods. Sometimes by up to a factor of 10. Pretty good. Okay. These are more details. Okay. Any questions on linear system solver? I guess sort of my view of this is, we know how to solve linear systems faster for when the system involves data. Then, think about the problems that you're working on. Think about where are you solving linear systems, because they're all over. If that linear system involves a data matrix, this is really a technique that you might want to try. It can be very powerful.
Hi, Professor.
Yes.
I think this is very interesting. Actually, we're working on in a high dimensional problem. When your matrix A, I'm thinking about if your matrix A is not like a square, but it's underdetermined, meaning your observation is much smaller than your dimension. Are you aware of any possibility we can do some preconditioning for that kind of matrix using your techniques here?
Yes. So of course, if you move to the normal equations, right, then that's always a square system. So you can apply this. You can work out a version that sort of directly does the same thing on the rectangular system using a left preconditioner. And the math actually works out very similarly. If you want to talk about that, I'd be happy to talk about it. I have notes written on it, but we don't have a paper on it.
Okay, thank you.
Any other questions? There's a kind of funny thing here, which is that, in general, right, the sort of dogma of numerical analysis is never form the normal equations, right? But these randomized low rank approximations work better when there's stronger spectral decay. And if you square things, you're going to get stronger spectral decay. So it's kind of strange, but the randomized preconditioner works better if you like form the normal equations. Okay, there might still be good reasons not to do that, but you have to weigh, weigh the pros and cons. It's not obvious anymore. Okay, nice ADMM. Okay, so now we're looking at a different class of problems. This is an example of, how do I plug in my linear system solver? Okay, so let's suppose I'm looking at this problem: minimize a loss function applied to AX plus a regularizer applied to X. Okay, so A is a linear map, L is smooth, and R is proximal. What I mean by proximal is that it's easy to compute a solution to the output of the prox operator, which requires computing an argument of the regularizer together with a quadratic term. Okay, so you never use these methods when you have to actually use an iterative method to solve this prox problem. So we're thinking about problems where this prox, there's like a closed form solution for the prox. For example, if the regularizer is the 1 norm, then prox is just a soft thresholding operator. If the regularizer is a 2 norm, it's just shrinkage. Okay, and if it's an indicator of a convex set, it's just projection onto that set. Great. So, and as an example, we got the lasso problem. We're minimizing ax minus b squared plus some regularization parameter times the 1 norm of x. This is to get sparse solutions to linear equations. Okay. Other examples are things like regularized logistic regression, support vector machines. There are like portfolio optimization examples. It's a pretty general template, actually. Okay. Here's our approach. The outer iteration is going to be the alternating direction method of multipliers, which is a very popular first order method in optimization. And then the inner iteration is going to require us to solve a linear system, which we're going to do with NIST and PCQ. Okay, so here's the idea of ADMM, okay, which many of you may have seen, but I want to, some of you may not have seen, yes? Okay, so it involves 2 minimizations. One is a minimization over of the augmented Lagrangian, is one way of looking at this. So one is minimizing the loss function L plus a quadratic term. The second is minimizing the regularization R plus a quadratic term. And then there's a linear update. Okay, you repeat this, you get an X star that nearly solves the problem. Okay. The Z minimization is easy. It's just a prox operator. So we're assuming it's closed form. The X minimization is hard because it involves the data, okay, this data matrix A. That's somehow the hardest part about it, is that every time we touch the X subproblem, we have to operate with the data matrix A. Okay. A good solution is to use inexact ADMM. So just first to notice that we don't need to exactly solve the X subproblem. It's okay if we do it with error like epsilon K at each iteration. The overall ADMM iteration will still converge as long as these errors are summable. Okay. Now, we can add randomized numerical linear algebra. We'll use NIST and PCQ to speed up that X minimization. So here's the idea. If this loss function L is twice differentiable, let's write down an approximation to the objective near the previous iterate xk. This is going to look a lot like sort of motivation for Newton's method, okay? So L of A times X is going to be L of A times XK plus the difference between X and XK times the gradient of this loss function at XK plus a second order term, okay, which is going to involve the Hessian of the loss function at XK. Okay, I'm writing it out like this to really separate where does the data matrix appear and where does the loss function appear, okay? So with this approximation, the X minimization becomes a linear system, right? If we minimize this approximation instead, okay? What we need to do is we need to find X so that this matrix, right, which sandwiches the Hessian at the current iterate in between A transpose and A, plus rho times the identity, X is equal to RK, where RK is some kind of residual. Okay, that's straightforward to compute. So the hard part is solving this linear system, okay? And the linear system involves the data matrix. Okay, that's good. We're actually in good shape. Should also remark that actually the the Hessian at the current iterate. Of course, if the loss function L is quadratic, this part is constant, okay? It's like identity or like 1/2 identity, okay? So we don't actually need to recompute an approximation for this thing at every iteration. We can just keep using the same one because this is constant. It's the same throughout the entire ADMM sequence of iterations, okay? Even if it's non-constant, we could use a preconditioner that's based on the Hessian at the previous iteration, right? As long as we haven't moved too far, it's probably still pretty good, okay? So we can actually save a lot of time by reusing the same Hessian approximation. Okay. Here's how the overall algorithm looks. At each iteration, I compute this residual. I use Nystrom PCG to find an epsilon approximate solution to this linear system, okay, which is regularized by rho, right? Which is think of it as the ADMM step size. It's like a step size on the dual. I solve this prox problem over Z, and then I do this linear update of the dual variable U. Okay. Repeat this enough times, I find an X star that nearly minimizes the system. People often worry about how to choose rho for ADMM. It's sometimes difficult, you know, to tune this parameter. And what's kind of interesting here is that rho plays not only this role of the dual step size. I'm sorry, I've sort of scaled the problem so you don't see it, but it's really playing a role of the dual step size. But it's also appearing here in the linear system. And we know that this linear system gets easier to solve when rho gets bigger. Okay, so although you still have the same problem with ADMM, that the number of iterations might depend on rho, here you've got this bias that you know that as rho gets bigger, it's going to get easier to solve a linear system. So every iteration through ADMM is going to get faster. This can be a reason to increase rho and actually make it much easier to choose rho. There's like a much sort of wider space of rhos that are reasonable because of this. Okay. Let me show you some numerics. I'm going to compare on 3 different problem classes: lasso, logistic regression, and support vector machines. And I'm going to compare with a bunch of state-of-the-art methods on lasso, including a Newton-based method. So you should expect it to get to higher order accuracy, but maybe be slower at the beginning. A matrix-free interior point method, and GLMNet, which is a coordinate descent method. Okay, so these are like specifically designed for the lasso. Logistic regression, Saga is currently sort of the main method people would use for logistic regression. And for SVM, we'll compare to libSVM, which is a sequential minimal optimization, which is basically like pairwise coordinate descent. So I think the thing I want you to notice, these are all very different kinds of algorithms. Okay, and they're all, you know, pretty carefully tuned, whereas we're just using, you know, what I would call sort of a, you know, jack of all trades like ADMM. Okay, we're picking data sets that have more than 10,000 rows or columns from a bunch of repositories. We are using a random feature map in order to generate even more features, just to make the problem like large enough that it's reasonable to use these methods. Okay, same stopping criterion and same parameter settings as the standard solver for each problem class. And we're using a constant sketch size of 30. Okay. So here are the results on lasso for a single data set. You can see that nice ADMM is performing as well or better than all of the other solvers until you're looking for solutions that are with stopping criteria smaller than 10 to the minus 3, which for lasso usually would stop at more like 10 to the minus 2 or even 10 to the minus 1. Okay. Yeah, you can see GLMNet, which is probably the most standard solver, does best for low accuracies. And then the semi-smooth Newton augmented Lagrangian is catching up and getting better for very high accuracies. That's to be expected because we're using a first order method. Okay, across many data sets, if we want to get to a moderate accuracy solution, you'll see that nice ADMM is, again, sort of faster by like sometimes up to a factor of 3 compared to other methods. For L1 regularized logistic regression, again, we're getting times that are much better than Saga. Factor of 2, factor of 3, up to a factor of like, the worst one was 5 or something for this problem. Okay, so we're doing better than Saga, which is actually also weird because it's not doing anything stochastic, right? It's actually computing like full gradients of things, which is a sort of wasteful, because you have a large data set, you should be using, subsets of the data set. They already give you enough information. You shouldn't be bothering to compute full gradients. Okay, I'm going to fix that in the third part of the talk. Okay. And for SVMs, I think this was probably the most surprising. The libSVM is written in C. Nice-ADMM is pure Python, okay? But we were still getting results that were 5 times faster, okay? And that's largely because, it's leaning so much on the linear algebra, there's not very much Python in it, actually. But it's still kind of remarkable. So we're, up to 5 times faster. Sorry, greater than or equal to 5 times faster. On every data set we tried, we were at least 5 times faster, okay? Anyway, I found this very surprising, without tuning ranks or anything. Okay, any questions on Nice-ADMM? So we're plugging in our linear system solver, and we're finding an algorithmic framework into which we can plug the linear system solver. And this linear system solver is so fast and takes advantage of the structure of the data so well that this framework ends up beating much more tailored algorithms for all of these different problem classes.
Professor?
Yes.
Is there any rate analysis for Nice-ADMM? For example,
there's a tiny bit of analysis in that paper that was published at ICML last summer. We are about to release much more extensive analysis. So I want to say, don't look at the analysis yet. Wait 2 weeks and then look on archive.
Okay, cool.
We have a much more sort of generalized version that takes into account, because there are 2 things that we're doing. One is that it's inexact, and the other is that we've sort of linearized part of the objective, and we weren't able to find a sort of complete analysis of that setting.
Okay, cool. Sir, what about do you also compare with, for example, lasso problem? We will have the ground truth instead of the optimization error. We'll have the iterate comparing to the ground truth. Do you have that kind of or experiment or?
I haven't done that kind of experiment. I guess sorry, this is a philosophical conversation, but I started to not believe in truth. Sorry.
Maybe we can talk offline. Sorry.
But yeah. Yeah, I don't know. Do you believe that the world really is sparse, or do you believe that it's just a good approximation to the world? I mean, for most of the settings actually where people apply lasso, I view it more as a method to find, let's say genome-wide, GWAS, genome-wide association study. I don't actually think that the effect of most genes on anything is 0. I think that there's super complex interactions, right? This is my belief about the world. I think there are crazy interactions, and every gene is, there's just these tiny little hydrogen bonds or whatever between this, or they're wound about around the, anyway, they're wound up in crazy ways. The folding of the chromosomes depends on everything a little bit. I don't think that there's actually sparsity in that problem, but it's a good approximation, and it allows you to pull out some interesting and kind of independent effects that you might want to investigate with knockout studies that are expensive and require you to experiment on animals or something. Okay, so what I actually find this in sort of most of the settings where people look at lasso, I don't really believe that there's true sparsity there, but you want a sparse solution anyway. So this is why, as a general, I don't like comparing with ground truth sparse solutions, because I don't really believe in them.
Okay. Thank you.
Yeah. Any other questions? Okay. Let me tell you a little bit about sketchy SQD. Okay, so let's move to the setting. We're going to consider an empirical risk minimization problem. Okay, so we want to find a W that minimizes the sum of Fi of W. So think of each of these Fi's as coming from a distinct data point. It might be, this might be a logistic regression problem. It might be a deep learning problem, something like this. Pretty typical method is stochastic gradient descent. At every iteration, I grab a vector G that somehow approximates my gradient. Maybe it's a mini batch gradient on a subset of samples. And I go in that direction, okay? This probably works as long as the expectation of G is actually equal to the gradient, okay? Great. That's all well and good, but what if the problem is ill-conditioned, as is typical in machine learning? Okay, well, you'd rather do something that looks a little bit more like a Newton method, right? That uses Hessian information to deal with the ill condition. Okay, so a natural idea is to say, you know, I want some kind of stochastic quasi-Newton method where I'm going to go in the direction H inverse G, where G kind of approximates my gradient and H kind of approximates my Hessian. Okay. Why would I do this? I should expect faster convergence. I should expect it to be more robust to ill conditioning. And it should be easier to choose hyperparameters like the learning rate. Okay. Because like for a Newton method, just like, I don't know, an eta that's like a little bit smaller than 1, as long as the, you know, the Hessian is like changing crazily quickly, is like fine. It's much harder to choose learning rate in first order methods. Okay. Cons are, of course, that the actual Hessian is very expensive to compute and very expensive to apply. So if I want to do something like this, I need to use a bunch of approximations. So here's a list of a bunch of approximations that different people have used in order to generate stochastic quasi-Newton methods. Okay, so first is, let's compute the Hessian on a data subsample. Second is, let's compute the Hessian from stale data. Okay, so let's, you know, compute it on a data subsample, and then let's not update it as our iterate changes. So we've moved away from the point where that was the subsampled Hessian. Now it's something else, but it's close enough, as long as the Hessian isn't changing quickly along the optimization trajectory. Okay. Some people form the Hessian approximation using a secant condition. This is the most classic, like quasi-Newton method, BFGS or LBFGS, that are used quite commonly for problems where you can exactly compute gradients. These work very well and very robustly. If you've got approximate gradients, they can severely mislead you. Because you can sort of form an entire idea of sort of globally what the function is doing from a noisy gradient that you can't trust, and it can actually not do so great. You could do it by a diagonal approximation. So Ada Hessian also uses randomized numerical linear algebra ideas to form a diagonal approximation to the Hessian. You could do a block diagonal Kronecker approximation, so that's a little bit more fancy. And you could also use a low rank approximation. So I'm going to tell you about using the low rank approximation. And maybe you should expect in the same way that sometimes your Jacobi preconditioning actually performs worse than no preconditioning for linear systems, and low rank preconditioning performs better. You might expect that there are problems on which the low rank preconditioner works much better than this diagonal or block diagonal preconditioner. So here is our oracle. Okay, so again, we should probably not be computing Hessians even on subsamples, okay? But we can form a sketch of the Hessian without ever computing a Hessian, okay? So remember the basic primitive that we need in order to compute you know, our low rank approximation is a matrix vector product with the matrix that we're approximating, okay? So here's how we're gonna do it. First, we're going to take a mini batch of samples, so some subset S of all the data points, and we're going to look at the mini batch loss tilde F, which is the loss on that set of samples. Okay, we can compute a mini batch gradient using automatic differentiation. Okay, so this is built into you know, any of the deep learning toolboxes like PyTorch or TensorFlow or Keras, et cetera, et cetera. It takes time, basically twice as long as just computing the function value itself. Okay, so think of this as easy and cheap. Okay, now we're going to define a mini batch Hessian vector product with vector v. Okay, so the Hessian of tilde f applied to a vector v is just the gradient of our mini batch gradient applied to v. Okay. Now, if I use automatic differentiation, right, on this function g tilde g of x times v, I will get my output is the Hessian vector product. Okay, so I need 2 passes of automatic differentiation. So you should think about this like about 4 times the cost of a function evaluation. Okay, so I can form my stochastic Hessian vector product. It takes me about 4 times as long as evaluating the function itself on the same subsample of data points. But probably, I think that's like the most critical idea. Okay, so here's what I do. At each epoch, now, I mean, this is a parameter, right? If you think the Hessian is changing quickly, you should do it more often. If you think the Hessian is not changing very quickly because you're not moving very far with your iterates, you can do it less often. Okay, you'll sample a data batch and use that data batch to sketch the subsampled Hessian. So here's the subsampled Hessian that I've written down. You're going to sketch it using automatic differentiation. You're going to use that sketch to form a rank R approximation of the Hessian. At every iteration, you will sample a data batch, form a gradient estimate. Okay, so this is your mini batch gradient. And then your step is going to be a regularized Hessian inverse applied to that gradient. Okay, remember, right, low rank plus multiple times identity, easy to apply the inverse to a vector. Okay, so that's the idea. Computing, all these steps are easy. Computing the search direction requires order p times r flops, where the dimension is p, that's the number of features. The cost of a fresh Hessian approximation is however many samples you're using for that Hessian approximation, plus r squared times the latent dimension p. And given a Hessian approximation, the per iteration cost is the number of samples you're using for the gradient approximation plus r applied to the number of features p. Great. So those are all, I mean, really acceptable costs. It depends on the R as well, right? So it depends on the rank you're choosing. It doesn't matter what rank you're choosing. The experiments here were done with rank 50 to rank 100. I'm going to show you some experiments. This leads to a per iteration cost that's like 30% more than stochastic gradient descent or ATOM. It turns out, though, if you decrease the rank, my students did this after they like put the first paper on archive. But if you decrease the rank, actually you get nearly as good performance. So you can get down to like rank 10, rank 5. It's like almost as good. And that's because the spectral decay is so strong at the beginning that just dealing correctly with the first part of the spectrum is the most important part. Okay. So that's good news because it means it's like not a lot of extra computation needed to handle the worst part of the L conditioning that's really messing with your convergence and with your stability. Okay. I'm going to skip any analysis. I'm skipping all the, but it's actually, I find it kind of remarkable. We have an analysis of this stochastic quasi-Newton method for a non-convex setting. Like, okay, there's the fact that you can write that down is remarkable. It uses the PL condition, Polyaklo-Bashevitz, and it assumes that your learning model is sophisticated enough that it can actually interpolate the training data. Okay, but that's actually a common setting in practice these days. So this is not, totally, vacuous theory. Okay, and you actually show that you get linear convergence in that setting. Okay, it's easy to select parameters, and we're choosing parameters consistently without a lot of fussing. Okay, I'm not going to go over the slide in detail. We've got a bunch of experiments, and it's across all the experiments. Kind of the same performance. So since I'm close to time, I think I'm going to walk you through one of these. So the basic thing that we want to assess is it doing on average about as well as SGD and ATOM? And 2, is it as robust or more robust than SGD and ATOM? Okay, so to show that, all of these plots, you're going to see the median plotted as a dark line. And you're going to see an interquantile interval, 75th percentile interquantile interval plotted with shading. Okay, these overlap, so it's a little bit hard to look at them. But the basic, so here's the basic fact. So for example, in the first one, SGD is this red line, the red area. So you can see it's huge, right? It goes all the way up to, 75 and all the way down to 55. Okay. Atom also has a very large interquantile interval. That's the sort of green area. And sketchy SGD has such a small interquantile interval that you can barely see it. It basically looks like it's all on top of that line. Okay. So in other words, and this is over sort of different choices of step size. Okay. So it almost doesn't matter what step size you choose for sketchy SGD, you get similar performance, whereas it matters quite a lot, and you should invest in hyperparameter tuning if you're using SGD or you're using Atom. Okay, so this is true on the Higgs data set. This is true on the mini-moon data set. This is true on the Volkert data set. Okay, over and over and over again. The peak performance that we get with sketchy SGD, actually here we're getting slightly better peak accuracy, or maybe comparable peak accuracy right to the top of the interquantile region for Atom, right? But we're doing better median, and certainly the bottom 25th percentile is much better. Okay, so more robust and about as fast. Here it's in terms of epochs. We also have a plot as a function of time. You can see the test set accuracy as a function of time. Maybe you want to check that we're not overfitting or that we're not generalizing worse than other methods, because deep learning is not actually an optimization problem, it's actually a generalization problem. But in fact, it's generalizing about equally well. So it's not overfitting worse than standard methods. Okay, and you see kind of similar performance. The interquantile range is small compared to the other methods, even as a function of time. Great. Tabular data classification, you see similar performance. Sketchy SGD is slightly higher, smaller interquantile range. Image classification, similar performance. Here we're comparing also to Atom W. Okay, sketchy SGD is the blue line. Again, comparable for performance, smaller interquantile range. Okay, this gets kind of boring, but okay. Compared to other quasi-Newton methods, what are we getting? It is getting better test accuracy than most other quasi-Newton methods. One exception is KFAC on the Volkert data set is doing slightly better than sketchy SGD, but KFAC also is somewhere between 2 and 10 times slower than sketchy SGD. So that's a downside. We're pretty pleased about this, that you've got a way of doing stochastic quasi-Newton. So you can deal with ill conditioning of these large-scale machine learning problems very efficiently, right? If you take the rank down to 5 or 10, it's really not much more expensive than standard stochastic gradient, and much more robust. Okay, I'm basically at time. So what's the big picture idea? Low rank structure is everywhere in machine learning data science problems. These matrices always have strong spectral decay at the beginning. You can use that to accelerate all sorts of optimization and learning algorithms. Okay, you can use it to accelerate top K eigenvalue decomposition, regularized linear system solves, composite optimization, stochastic gradient descent, and we're not at the end of the list. We're definitely not at the end of the list. So this is something I'm very excited about. I've got sort of lots more ideas for algorithms you can speed up. If you want to talk about speeding up your favorite algorithm, I would be very glad to chat. So just reach out. Thanks for your attention, and happy to take questions.
Awesome. Thank you, Madeleine.